Hello guys, this is Dave. Today we will study about gravitational fields and Kepler laws, okay? So about gravitational field, if we have a mass m and we have to calculate field at point P, which is at a distance r from mass m, this is the unit vector r. So the gravitational field, if I state it to be E, this would be because the gravitational force is attractive force, as I have cleared it in my last video, and field is written as F by m. Okay, you can see it in my last video. So this would be F by m naught, because if I place a test mass over here, the force experienced by this test mass would be m naught by r square r, and this would be negative since force is attractive. So field would be F by m naught. So this is purely the field by the mass m. M naught is not involved here then. So this would be minus g m by r square r. Okay. This is a vector and this is the direction, and since this is negative, so this is inward. Okay. Now let us take, for example, a ring. So in a ring, what happens, say if this is a ring and inside this is hollow. Okay, this is a two-dimensional figure and inside this is hollow. You have to calculate the field at a point P. Okay, now this point P is at a distance r from the center of the ring. Ring has a mass m. So how do we calculate it? And ring also has a radius. Suppose the radius is capital A. How do we calculate the field at point P? You see, first we have to take the element mass. For example, if we take this is the element mass. Since the ring is two-dimensional, mass would be directly proportional to the area. Okay, so the element mass dm would be equal to, this would not be the area, this would be the length. Yeah, since ring is hollow, I have to take the length. So dm would be m by the length of the ring, which would be 2 pi a times the length of this element mass. Okay, so if I draw it out here clearly, this is a portion of ring I have taken, this is the element mass, this has a length, say dl. So this would be m by 2 pi a times dl, and this makes a very, very small angle, say d theta. Alright, this is a. So as we know, for a curve, dl would be equal to a times d theta, right? So dm would be equal to m by 2 pi a times a d theta. A would get cancelled out, dm would be equal to m by 2 pi times d theta, right? Okay, so we have the element mass now. So what do we do now? We can see that the gravitational force at P due to this mass or gravitational field would be directed along this line. Okay, and this would be inwards. And if we take a similar mass due to symmetry, this field would also be directed inwards. Okay, and what would this field E be? Well, this field E would be equal to G dm by, suppose this distance is z, then this would be G dm by z square. Okay, alright, field would be G dm by z square. What is z? By Pythagoras theorem, we know that z is root under a square plus r square. Okay, by Pythagoras theorem, z is root under a square plus r square. So E would be equal to G dm by a square plus r square. Okay, we're not done yet, because fields are distributed and I have to find out the net field. So what do is I resolve these fields, and if we resolve these two are particular examples. Since symmetry will follow, if these two have been cleared out, the symmetry will follow as such. So I have taken the two fields. Since these are similar due to symmetry, the vertical components of this field shall cancel out. Okay, only remains is horizontal component, and this is the differential field, sorry, dE, because the mass is dm. Yeah, all right. So what would be the net E? The net E would be equal to, since these are differential fields and they resolve only along the line OP, let us suppose this angle is alpha, they resolve along the line as d cos alpha. Okay, so E would be equal to integration g dm by a square plus r square times cos alpha. Alright, now you see alpha, you see, let me draw the figure over here. This is OP and this is angle alpha, this is A and this is R, this is Z. So cos alpha would be equal to base by hypotenuse, R divided by Z. What is Z? Z is root under A square plus R square. So we did d cos alpha, right? So we had g upon A square plus R square times dm. What was dm? Dm was m divided by 2 pi a times, sorry, a got cancelled, m by 2 pi d theta, right? And this would be times cos alpha, this would be root r divided by a square plus r square, and this is E. We should integrate this, 0 to 2 pi it will go because theta is of the ring. Alright, theta is not alpha here. Don't confuse theta with alpha. Theta is not equal to alpha. Alpha is a different thing. Theta is a different thing. Theta is for only measuring the angle along the ring. Alright. So theta will go from 0 to 2 pi. This cancels out. So we are left with gm r divided by a square plus r square to the power 3 over 2. Alright. And in r, so r cap, right? And this would be minus. Alright. This is the net field. This is the field we are looking for. Alright. Since we have resolved it along OP direction, this direction is r cap. So the attracted direction, this would be negative, so negative r cap. Okay, this is the correct answer. Okay, so this is the modulus of P, this is the modulus, and this means this is the absolute value. Now I want to ask you basic questions. For example, if r reaches infinite, what will be the value of E? Since when r reaches infinite, the numerator tends to infinity, denominator tends to infinity. Expression becomes infinite by infinite, which is not defined. Okay. So we apply the theory of limits over here. Okay, see how mathematics comes into play. GMR, we can divide the denominator by r square, or we can take this r square as common. So when we take r square common, we are left with 1 plus a square by r square. Okay, this would be 3 over 2 and this would also be 3 over 2. So 2 gets cancelled over here. Alright, so E becomes GMR by R cube, 1 plus a square by r square to the power 3 over 2. I can cancel r from r cube over here and we are left with r square. Alright, so the expression now becomes GM by r square times 1 plus a square by r square to the power 3 over 2. Now when r reaches infinity, this expression becomes 0, because 1 by infinite is 0. So 1 plus 0 is 1. So incidentally E is only proportional to 1 by r square when r reaches infinite, and when this happens, this becomes 0. So when r reaches infinity, E is 0. Okay. When r equal to 0, E is 0. Alright. You see, this is the concept of limit. We could also have, do this by L'Hospital's rule. What happens in L'Hospital rules is you differentiate both the numerators and the denominators separately and then apply the limits. Okay. For example, if E is GMR by a square plus r square to the power 3 over 2. And I want to find out limit r reaches infinite. Limit r reaches infinite. So what I do is I separately differentiate numerator and denominator. So we have, by differentiating numerator with respect to r, we have gm, and by differentiating this we have 3 by 2 a square plus r square, right, times this would be actually 3 by 2 minus 1, this would be, because we are differentiating, so we are left with 1 over 2, right, and this would be times 2r. Alright, this cancels out, and now again we can divide this by, we can take r square common. Alright, so we are left with, by taking r square common, we are left with 1 plus a square by r square to the power half times r square, because r will be out, r square root will be r, and this will be multiplied by this r, and this will be r square. So we are essentially left with the same expression. You see, this is the same expression, and when we apply limits now, limit r reaches infinite, so we have 0. Alright, okay, so now we return to another problem which is of disk. Okay, now I want to find out the gravitational field due to disk of mass m at a point P which is outside the disk at a distance r from its center O. Okay, first of all I want to remind you that I have already plotted E versus R, okay, for ring in my last video. Okay, if you wish to see the plot of E versus R for a ring in my last video, you can see it. Now I am going to solve for a disk. Okay, so what happens is, in a disk, this space is filled, okay, is not hollow. Since this is filled and this is not hollow, this means mass is distributed, and since this is filled, this means mass is distributed along a area. M is distributed along area. So if we have to take an element mass m, that element mass m must be dependent on the area. Okay, so what we do is we divide disk into thin rings. Alright, okay, we have divided disk into thin rings. This is ring 1, we can assume another ring 2. So I am assuming this ring. Alright, now what will be the mass of this ring? Well, the mass dm of this ring would be equal to the mass of disk divided by the area of disk, which is pi a square, times the area of this ring. What will be the area of this ring? Area of this ring will be the circumference of the ring times the width. Okay, so suppose this is a ring. This has radius x and a width of dx. Okay, I am just assuming. Okay, this is x and this is dx. So what will be the area? This will be 2 pi x times dx. Area is circumference into width, na? So pi gets cancelled over here. So dm would be equal to 2m divided by a square times x dx. Okay, this is the element mass. Alright, now I have already written the formula for the electric field, for the gravitational field for a ring. Okay, that formula was gmr by r square plus a square to the power 3 over 2. This was the formula for the gravitational field of a ring. So I have just to assume this formula now for this ring. So since the ring is specific, the mass will be dm. Okay, so this ring will have gravitational field dE, and this would be g dm r by r square plus a square to the power 3 over 2. Okay, you see this field would be already directed towards here, because for a specific ring I had directed this field by taking the components. Okay, since field was like this for this ring, but in the nutshell the component came along the line OP. So this field dE g dm r by r square plus a square is already along OP. Okay, now we do not need to resolve this field. Okay, you will do a blunder by resolving this field. So now let us calculate dE is equal to, this would be G, what was dm? 2m by a square x dx, right? R by r square plus x square to the power 3 over 2. Alright. Now we have to integrate this. Now we can integrate this. Alright. Since r and x are independent of each other, r and x are independent. Alright. So E would be equal to 2gmr by a square. This would be integration of x dx divided by r square plus x square to the power 3 over 2. Now since x is a variable here, x will go from 0 to a, because rings are divided inside the disk. So the maximum radius that they can reach is of the disk only. So x will go from 0 to a. Alright. So how do we do this integration? This is very important because it will come in maths. I can be sure. So what we do is, we first substitute it trigonometrically. Either we can do trigonometry, or we can just assume this r square plus x square as somewhat z. Alright. For example, if we assume r square plus x square to be z. Alright. Let us assume r square plus z square to be x square to be z square. Alright. So when we differentiate this, since r is constant, only x is varying, we have 2x dx equal to 2z dz. 2 gets cancelled out, x dx is z dz. We are just substituting the value of x dz as z dz. What was r square plus x square? Z square. So z square to the power 3 by 2 will be z cube. Z cancels out and this will be z square. Alright. Now limits will also change because x is varying here. Since we are integrating now with respect to z, we will have to put the limits of z. So when x equal to 0, this would be r square root, which would be r. Okay. And when x would reach a, this would be equal to root under a square plus r square. Alright. This would be the limits of z. Alright. So E was 2gm by a square r. This would be dz by z square, right? This would be dz by z square because z and z cube cancel out, and this would be from r to root under a square plus r square. So what is this integral? This is minus 1 by z, okay? You will have to remember this. This would be minus 1 over z, and this would go from r to root under a square plus r square. Alright. So this would be 1 by root under a square plus r square minus 1 by r, and since minus sign is outside, so we have this answer as 1 by r minus 1 by root under r square plus a square. Alright. And this is 2gm r by a. Alright. Now what we do is, we take this 1 by r as common. So we are left with 2gm by a 1 minus r divided by root r square plus a square. Alright. This is the more generalized answer. And also I have to say one thing about this expression, r divided by r square plus a square. You see, for a ring, for a we can say, for a disk only, this was a and this was r. Alright. Suppose this angle is theta, so cos theta will be r divided by r square plus a square. Okay, so you can substitute as cos theta, but I mean this has no significance. So this is the answer. Okay, for the field, this is the answer. Alright, so I have the field now, and the field varies like this. So now I want to plot E versus R. How do I plot this? You see, first of all, when we plot something, we draw two axes. One is what we are trying to plot, and other is against what we are trying to plot. So we are trying to plot E against R. Okay. Alright, so when r reaches 0, this is the origin. When r is 0, this means since r square plus a square will give a square, and this is 0, so E would be 2gm by a square. So here this would be the value of E, this would be 2gm by a square. Okay. Now what happens if r reaches infinite? When r reaches infinite, this expression can be written as 1 plus root under 1 plus a by r whole square, right? So this would be 1 minus this and 2gm by a square, this would be E. So when r reaches infinite, this means a by r would be 0. So this we would be left with 1 in the denominator and 1 minus 1 would be 0. So E would be 0. Alright. Now we have two things. Now I want to know what is the curve. To know the curve, we have to find out what is the differential of E with respect to r. Okay. If this is positive, then that means curve is upward sloping. Alright. If this is negative, then that means it is downward sloping. Okay. Since when E is reaching 0, when r is reaching infinity, the most probable thing is that curve is downward sloping. Okay, but you cannot draw a curve just like this, because it may have some maximum after which it is down sloping. So first we will have to see if there is a maximum or not. Okay, so for the condition of maximum or minimum is that at any point the slope should be 0. Okay, this is the basic condition. So I want to see first whether the slope becomes 0 or not, or is it continuously down. Okay, so when we differentiate this, we have 2gm by a square and 1 will go out, this will be minus. So this will be differential of u by v. Okay, so this would be v du minus u dv by v square. You have to remember this, and the differential would turn out to be like this: root r square plus a square times 1 minus r divided by root r square plus a square times 2r, and this would be 2, right? So this would be 2r square, 2 gets cancelled out, and in the denominator this would be r square plus a square. Okay, so I am just writing the numerator now. Denominator, it does not need to be written. d by dr would be equal to 2gm by a square. We are taking this upward, so we have r square plus a square minus r square. Okay, so r square will get cancelled out. So we have a square root. So this would be no, this would not be root, because root times would be so this would be a square divided by r square plus a square to the power 3 over 2, and this would be minus, right? A square gets cancelled out. So you see the differential dE by dr is minus 2gm by r square plus a square to the power 3 over 2. Nowhere this differential is 0. This means neither this curve has maximum nor this has minimum. It is continuously down sloping. This means the curve must be like this. This is the curve. Okay. Curve has to be down sloping because slope is negative. And also E reaches 0 when r reaches infinity. E cannot reach 0 when r reaches infinity. The curve is upward sloping. Alright. This is the answer. This is the plot of E versus r for a disk. Alright, so now I want to find out the field due to spherical shell. Suppose this is the spherical shell. Okay. Since this being a shell, inside the shell this is hollow. So mass is dependent on the area only. Let us take a point P over here. This is the center of the shell. This point P is at a distance r. Okay. So now I want to find out the field due to this shell. How do I do it? First, I divide this shell into ring. Sphere can be divided into ring if it is a shell. Okay. So let us say this is the center of the ring. Suppose this is a point A, and suppose the radius of the sphere is small a. Alright. Let us say this is angle theta, and this is a very small bit, so I am taking a very small angle d theta. Okay. And this is the radius of the ring. Okay. And this is the distance of the ring from the point P. Let us say this distance is z. Okay. So what is the radius of the ring? If this is the radius r, then by Pythagoras theorem we can easily see that sine theta is perpendicular by hypotenuse. Since this is 90 degree, so sine theta would be equal to r by a. So r would be equal to a sine theta. Okay, all right. We have the radius of the ring now. What is the width of the ring? Since mass is dependent on the area, if we calculate the differential mass of the ring, that would be circumference times width. Circumference would be 2 pi r, which is 2 pi a sine theta, times width. What will be width? This is width. Since this is a, this is d theta, width will be a d theta. Alright. dm would be equal to m by 4 pi r, 4 pi a square actually, times the differential area of the ring, right? So this dm would be equal to m by 4 pi a square times the differential area of the ring. Okay, a gets cancelled out, pi gets cancelled out, 2 gets cancelled with 4. So we have dm to be m by 2 sine theta d theta. This is the differential mass of the ring. Okay, now we have the differential mass of the ring. Okay, so now I want to calculate the gravitational field due to this differential mass of the ring. Earlier I had told you that for a ring, what is the gravitational force? What is the gravitational field actually? You see, for a ring I had calculated gravitational field to be g dm. If this was z, by z square, and if this was alpha, then cos alpha, if you remember. Okay, since the field resolved along this line for a ring, similar formula we can apply over here. If this is alpha, okay, so I can write the gravitational field due to this ring to be g dm by z square cos alpha. Okay, but dm would be this. All right, let me draw it here again. This is the ring, sorry, this is the spherical shell. Yeah, this is point O, this is point P, and this is Z. This is A, this is R, and this is theta, this is d theta, this is alpha. So the differential field D would be equal to g dm by z square cos alpha. Alright, so what is dm? dm is m by 2 sine theta d theta. So now I am just applying the principles of triangle over here. You see, if you remember trigonometry, it is said that when two sides contain an angle theta, then cos theta can be written as a square plus r square minus z square by 2ar. Just remember, how will we know that theta is contained between which sides? If a square plus r square by 2ar is there, then theta is contained between a and r. Okay, alright. A is constant, R is constant, because R will be constant for a particular sphere and a particular point. So I differentiate this cos theta, then we have minus sine theta d theta. This would be equal to, this goes away, this is constant, this comes out, this would be minus 2z dz by 2ar. Okay, 2 gets cancelled, minus minus gets cancelled. We have the expression of sine theta as z dz by ar. I am applying here the expression of sine theta d theta here. So d would be equal to g m by 2z square. Yeah, that would be z dz by ar. Alright, z dz by ar, that would be. So now what would be cos alpha over here? You see, if I want to calculate now cos alpha, since cos alpha is contained between z and r, so we can easily write cos alpha as z square plus r square minus 2zr by, sorry, z square plus r square minus a square by 2zr. This will be cos alpha. Yes, this is the exact expression for cos alpha. Alright, so what will be the field now? Here we have to write cos alpha also. So D would become gm by 4ar square. Alright, 4ar square times 1 minus a square minus r square by z square times dz. This would be the answer for field. Okay, how we can see, you see zz cancels out. Here we are left with gm by 2zar dz cos alpha. Now I am putting the value of cos alpha. So we have, there's not much space left over here actually. De would be equal to gm by, there's not much space. Okay, I'm writing it fresh. You see sin theta d theta was z dz by ar. Okay, also dm was m by 2 sin theta d theta, and de would be g dm by z square cos alpha. Now cos alpha was z square plus r square minus a square by 2zr. Now we just apply this expression over here. De would be equal to g times dm. What is dm? M by 2 sin theta d theta. What is it? dz by ar by z square. Okay, times cos alpha. Cos alpha was z square plus r square minus a square by 2zr. Alright, so z cancelled out, right? This would in turn, we take this expression as 1, so we have m by 4 a r square, and z would be z square, so we take z square inside, so we have 1 minus a square minus r square, right? 1 minus a square minus r square by z square times, this was dz na. This is the final expression. Okay, this is the final expression of this de. Alright, this is the final expression of d. Now we have to integrate this. So de was m by gm by actually 4ar square times 1 minus a square minus r square by z square dz. So integrate this. Okay, so this would be e, this would be gm by 4ar square integration of dz minus a square minus r square actually by z square dz. Now you see, for a shell, I want to find out the value of the variation of z. This was z, right? And this was the differential ring. This was r. So z can go from this point to this point in extremities if you want. You see, this will also be the part of the ring. If you take a small ring over here, so this would be the minimum value of z, and this would be the maximum value of z. Since this radius is a and this is r, so minimum value of z would be r minus a. Okay, this would be r minus a, and this would be r plus a, right? So z would vary from r minus a to r plus a. Okay, these would be the limits of z. Alright, yeah, this would be the limit of z. So E would be equal to gm by 4ar square z plus a square minus r square by z, and the limits would vary from r minus a to r plus a. Alright, let's calculate this. Gm by 4ar square. So r plus a minus r plus a, this would be 2a. Alright, plus a square minus r square by r plus a minus a square minus r square by r minus a. So this cancels out, a minus r into a plus r. So this would be a minus r into a plus r. So this would be plus a plus r, right? So this cancels out. Alright, so 2a plus 2a, 4a. Gm by 4ar square times 4a. So 4a cancels out, so we have left with gm by r square. This is the answer. Okay, in vectorial field, if we have to write, we have gm minus by r square r. This is the answer. This is the answer for the field outside the shell. If we want that the field should we have to calculate the field at outside the shell. This is the answer. Alright, so what happens if I want to calculate the field inside the shell? For example, if this is the point P and this is the distance R, how do I do it? I use the same expression, okay. E would be same, gm by 4ar square times z plus a square minus r square by z. After integration, this would arise, and that would be the same expression, only limits would change. Okay, since limit would change, because you know this is a, so the field would vary from this. Okay, so this would be a minus r to whole of this, this would be a plus r. So we have a minus r to a plus r. Actually this should be the limits. Alright, so E we have gm by 4ar square, this would be a plus r minus a plus r, this cancels out, this would be 2r plus a square minus r square by a plus r minus a square minus r square by a minus r. So this cancels out, this is a minus r, this cancels out, this is a plus r. So minus would be a minus r, so this gets cancelled out. R plus r was 2r, minus r minus r minus 2r, so E would be 0. Alright, so inside the spherical shell E is 0. So in nutshell, I have the expression E equal to 0 when r is less than a. E is equal to gm by r square when r is greater than a. This is the final answer I have for field inside the spherical shell. If I have to plot it, it is very easy. This is E, this is E, this is R. I am plotting mod E, alright. And if this is A is the radius, so we have the field 0, alright. And then we have field equal to gm by r square. Gm by r square. So at A, the field would be, the graph would be like this. Alright, here it is only x-axis. Okay, the value here would be gm by a square. The value here would be gm by a square, and this would be the graph. Alright, calculate the field for a rod. Alright, rod has a mass m. Now mass m is distributed along length. Okay, m is distributed along length. So the element mass which we shall take shall be distributed along length. Okay. So now we have to calculate gravitational field at point P. P is at a distance r from O. So what we do is we take the element mass from the center of the rod. Okay. Let us say this element mass is at a distance x and it has a width dx. Alright. This is the element mass. So what is this mass? Let us say this is dm. This would be m divided by the length of the rod times the width of the mass. Okay. Since mass is distributed along length, as I have told you. Now the field which this mass will have will be directed along this line, and it will be inwards as the gravitational field is attractive. Okay. Let us say this is E. In a symmetrical position, we can take another mass, okay, and this can have the same field E. Oh, sorry, this would be D and this would be D, okay. So now let us take this angle to be as alpha. You see the horizontal components now would be cancelled out. This would be D sin alpha, this would be D sin alpha. For these element masses, this would be cancelled out. Only the vertical components will remain, and that too they would be inwards, okay, along the line PO. So the net gravitational field of this rod would be equal to D cos alpha integration. Okay. So what was DE now? You see DE. DE was G dm by, this was R, so G dm by R square plus X square. This was the differential field of the differential mass. This is integrated, and what is cos alpha? Cos alpha is base by hypotenuse. This means r divided by cos alpha is base, which is r, by hypotenuse. This means this would be like this, root r square plus x square, right? And what is now dm? So E is gr mgr by L dx by r square plus x square to the power 3 over 2. Alright, this would be integrated. Alright, so what would be the limits of x? Now I want to know what would be the limits of x. You see, x is from the center point, okay? So since center point is assumed to be origin, x can go from for this half of the rod, the right half of the rod, x will go from 0 to L by 2, and for the left half of the rod, x will go from 0 to minus L by 2. So in nutshell, x will go from minus L by 2 to positive L by 2. Alright, these are the limits of x. Okay. Alright, so E is mgr by L dx by r square plus x square to the power 3 over 2. This has been integrated from minus L by 2 to positive L by 2. Alright, mgr by L. Okay, dx. Yup. Now, how do we integrate this? You see, we cannot integrate this the original way because here x is not there. So if you substitute r square plus x square to be z square, x dx would be z dz, but x is not there, na? So you cannot integrate in the previous way which I did. So you have to assume another trick now. What is that trick? Suppose x is r tan theta. We go trigonometric. Suppose x is r tan theta. Alright. So what will be dx? Since r is constant over here, for a particular rod, this would be r secant square theta d theta. You have to remember the differential of tan theta. I can do nothing about this. I won't prove this now. And now what would be x square plus r square? You see, x was r tan theta. So this would be r 1 plus tan square theta is secant square theta. So this would be secant square theta. And what would be the 3 by 2? So this would be 3 over 2, 2 gets cancelled out. So we have r cube secant cube theta. Alright. So E is mg r by L integration. Forget the limits right now. So we have dx to be r secant square theta d theta by r cube secant cube theta. 2 gets cancelled. Here 3 and 1 gets cancelled. So we are left with r square and secant theta only. So the final expression of this is mg r by L integration. 1 by secant theta is cos theta. So we have cos theta d theta, and this would be 1 by, and this is r and this is r square. So 1 also would be cancelled out. So we are left with mg by L r. Okay. Integration of cos theta d theta. Alright. So mg by L r integral cos theta d theta. What is the integration of cos theta? You see, the differential of sin theta d by d theta of sin theta is positive cos theta. So we take this d theta over here, and now if we integrate this would be sin theta. So integration of cos theta is positive sin theta. So we have E to be mg by L r sin theta, which is positive sin theta, right? I am taking the modulus. I am not considering the sign over here. So now we have to calculate the value, the limits. Now we have to see the limits, or we can directly substitute sin theta. You see, x by r was tan theta, right? What is sin theta then? Sin theta is x divided by root under x square plus r square. It is as simple as that. What will be cos theta? cos theta will be r divided by root x square plus r square. If you divide these two expressions, you get the same expression as this. Alright, so we have mg by lr times x divided by root under r square plus x square. So E is mg by lr times x divided by root under r square plus x square. Now x will vary from minus L over 2 to L over 2. Okay. So we can just calculate the final value. This would be L by 2, right? This would be L by 2 by r square plus L square by 4 root minus of minus L by 2. So this would be positive by root under r square plus L square by 4. Alright. So this becomes L. L gets cancelled out. So we have E equal to mg L by L. L gets cancelled out. R root under r square plus L square by 4. Okay. So this is mg by r under root r square plus L square by 4. You see, dimensionally it is also correct, since the field was proportional to 1 by r square. So it is proportional to L to the power minus 2, length to the power minus 2, which is length. This is length square root, which is L. So L2, this will be L minus 2. Okay. This is the answer. So the final answer is mg by r under root r square plus L square by 4. This is the final answer. Okay, so this was the field. Now I want to plot E versus R. How do I do it? This is R, this is E. You see, when R reaches 0, this root under expression will be L by 2 times 0. So E will reach infinite when R reaches 0. When R reaches infinite, then infinite times infinite is infinite. So 1 by infinite is 0. So E reaches 0. So this is a very simple expression. Very simple. A very simple hyperbola. That is it. Nothing has to be done over here. This is the answer. This is the field. Okay. You see, E is reaching infinity when R reaches 0. And E is reaching 0 when R reaches infinity. This is the answer. Okay. Alright, so let's move on to the next question. Instead of being perpendicular to the rod, the point P is now along the length of the rod. Now I want to find out the field, the gravitation field at point P of the rod of mass M. You see, M is varying along length. Okay. So whatever mass element I take, it has to vary along length. Okay. So from the point O, I take an element mass. Okay, this has a distance x from point O and mass is dx. Length of the rod is L. Now, the element mass would be equal to m by L times dx. What is the distance of this element mass from the point P? You see, since dx is very infinitesimal, I neglect it, so it will be r minus x. Alright. So what is the gravitational field due to this element mass at point P? Well, this will be g dm by r minus x square. This would be the elementary gravitational field. So we can analyze it like this: gm by L at dx by r minus x whole square. We can integrate it to get the net field. The net field would be directed inwards. Okay. Now since the point is taken from the center O, the element mass is taken from center O, so it has to cover both the ends of the rod, I mean the left half and the right half. So the left half has a length minus L by 2. You see, if this is origin, then left half will vary from minus L by 2 to 0. And the right half will be varying from 0 to L by 2. So in nutshell, I can write it as this: minus L by 2 to L by 2. Okay. So now I take r minus x to be z. Since r is constant, dx would be equal to minus dz. So dx by r minus x whole square would be dz by z square negative. And this would be equal to minus 1 by z minus this would be plus 1 by z. Okay. So I have Gm by L, okay, Gm by L 1 upon Z, right? So Z would be R minus X, and X would vary from minus L over 2 to L over 2. This is E, okay. So E would be equal to Gm by L 1 upon R minus L over 2 minus 1 upon R minus L by 2. So this would be R plus L by 2, right? So R plus L by 2 minus R plus L by 2. So R gets cancelled and L by 2 is L. So L will get cancelled. So the final expression I will have is Gm divided by R square minus L square by 4. Okay, this is the final expression for the field. Alright. Gm by R square minus L square by 4. So before going through Kepler's laws, I want to explain you something. For example, this is the Earth. Okay. And this is the satellite revolving around the Earth. So I want to know why this satellite is revolving. You know, why this satellite is going around along the circle. If it goes along the circle at all, why this satellite is revolving. What is making this satellite revolve around the Earth? You see, the gravitational pull of the Earth is making this satellite revolve around the Earth. Okay, suppose this is a circle of radius r. Okay, so the force due to gravity is pulling the satellite inwards, but as it is going through the circle, so it is maintaining its orbit due to this force. So the force would be equal to Gme ms. Ms is the mass of satellite, me is the mass of Earth, by r square. This would be equal to the centripetal force, mv square by r. Okay, this centripetal force is responsible for keeping the satellite in motion, and this centripetal force is being produced by this gravitational force. Okay, so we can equate the two. This is the mass of satellite also, so ms gets cancelled out, r gets cancelled, so we have v equal to under root Gme by r. Okay, yeah, you see, this is the velocity of the satellite which revolves around the Earth. Okay, so these are the Kepler's laws of motion. Okay, this is the first law. First law states that the orbit of each planet is an ellipse with the sun at the focus. So this is the sun here at A. Here also the sun can be. This is another focus of the ellipse. Here is the planet. So planet, when it revolves around the sun, it revolves in an elliptical path, and the sun is at the focus of the elliptical path. Okay. Second law is the line joining the planet to the sun sweeps out equal areas in equal time. Okay. So you can see this area sector and this area sector. Okay. The two sectors have been drawn. You see, the rate of change of area of this sector and rate of change of area of this sector will be same. Alright, that's what it wants to say. Equal areas and equal time means rate of change of area, dA by dt, or A by t, delta A by delta t, whatever you can say. Third law is the square of the period of a planet is proportional to the cube of its mean distance from the sun. Okay, so the square of period, I mean the period of revolution, is proportional to the cube of mean distance from the sun. Alright, you see, I can prove this. This is valid for ellipse as well as for circle. So I am taking a very general case of circle, because in ellipse it will prove to be complicated. Okay, that will prove to be beyond the course. And alright, let me take it for a circle first. Alright, so this is the Earth and this is the satellite. I am assuming the satellite is going around a circle. Okay, so what is keeping the satellite around the circle? As I told you earlier, that was the gravitational force of the Earth. Okay, Gme ms by r square, that was responsible for producing centripetal force. This got cancelled, this got cancelled. V was root under Gme by r. Alright, so what will be the time period? You see, time period is distance upon speed. Okay, time is distance by speed. Okay, you see, as I already told you in my previous videos, and I think in my first video, when displacement is questioned, then velocity comes into play. But when distance is questioned, then speed will come into play. Okay. This here, the magnitude will be the speed. Okay. Although the velocity will have a direction. Okay. If we incorporate direction in this, then this will be a velocity. Otherwise, this is just the magnitude and hence it will be the speed. So what is the distance? Distance is the circumference of the circle, which is 2 pi r divided by root under GME times root r. Root r will go up. So this will be t. So okay, I am assuming this 2 pi by root GME as k. So t is k r to the power 3 over 2. So t square is equal to k square r cube. So t square is proportional to r cube. Okay. So I have derived it for a circle. Okay. T square is proportional to r cube. This is valid for any satellite, not just the earth, but for also sun. I have not taken sun because I had to take an ellipse then. So for a generalized example, I have taken earth and I have taken a satellite revolving around the earth in a circle. So t square is proportional to r cube. Okay. So guys, this was my analysis pertaining to gravitation. Okay. Do let me know if I have missed out anything. Alright. Please like, rate, review, subscribe. Thank you.